Hello, welcome to a slightly unusual video. I'm trying a new format of stuff. Going to be focused largely around VCV Rack in this. So this is a video where I'm going to dig in a bit on the øchd-expander, which launched a little over a year ago now. So it was a year last October. So it was October 2023 when DivKid himself was up in Glasgow. So we did an in-person event. I think during that event and surrounding content that we launched at the same time as the module, we covered a lot of bases in terms of what the module can do, what the design ethos was behind it, how to use it in patches. But there's a long list of content that we've kind of had on the whiteboard in terms of it'd be cool to showcase this, showcase that. So this is me actually getting around to one of these videos that I had in mind back then, and that is to kind of explore the nuts and bolts of this. So this will be quite a technical video where I'm going to go into the individual sections of the øchd-expander, dig into some of the circuitry to an extent. As the title of this video is no doubt clickbaity, it's probably something along the lines of DIY building an øchd-expander, which is not wrong. I'm going to use VCV Rack and I'm going to patch up an equivalent of the øchd-expander, just using largely the fundamental modules in VCV Rack, plus an oct, of course. This will be quite a fun one. I probably won't be too musical in terms of what the output is, because it's just going to be signal processing from LFOs. But whatever music is currently playing in the background is a patch I've not patched yet, so I'll do something after I've shot this, and hopefully make something pleasant to listen to in the background. So let's dive in. I'm going to load up VCV Rack. Here we go. Blank slate. That should be good to go. Should have. Yep, I've got all the Instruō modules and all the VCV fundamentals. So that should be all I'll need for this. Output, I'll need to state a device, even though we're not going to be monitoring much. Cool. And I can clear all that. So what we'll be using is an oct. There we go. That's our patch. And we're going to be recreating something that could fit in 4HP, but this definitely won't be 4HP. Let's look at our reference here. This is the quick start guide. There we go. So the øchd-expander itself, 4 sections. Top section is full wave rectifiers. We then have diode logic. We then have trigger extraction, and then the 4-bit DACs, which they're definitely the more intriguing part of the whole design, I think. So that's going to be quite fun to dig into. Let's just start at the top and work our way down. So first section here, we have 4 full wave rectifiers. So full wave rectifiers in general, are a really useful utility within modular. They do exist in the Instruō range. Technically the CSL has got a full wave rectifier in its multiply stage, where it can be applied either half wave for AM, so that's half wave rectifying the top signal. So if it's a sine wave, we're just going to get like the positive portion of that. Rect is full wave rectification. So I've got that base covered, but it's a particular underuse of the rest of the CSL. But yeah, the rectifier stage could be pulled out and used by patching signal in here, DC signal in here, and the output. It's a utility that probably exists in a lot of contexts within Eurorack. I'm going to be using a collection of different modules from the VCV fundamentals. So it's quite possible I'll be doing this in not the most efficient way. I'm basing this on patches that I just came up with when I was testing stuff out and prototyping, because the øchd-expander itself, I actually prototyped quite a lot of it in VCV Rack just to test the proof of concept of different signal processes. There may or may not be more efficient ways of going about doing some of these patches, but let me know if I miss anything hugely, or if there's anything that could be done more efficiently, because that's that's the best way to learn, is to share an approach and then learn from other approaches that other people take. So the compare module, which is largely, as I understand, it's a comparator, and normally you would have just sort of binary extraction. So it's like you set a threshold, signal breaches that, and you derive logic from that. But this has actually got variable outputs as well. So this is a starting point for rectifiers. So we can see here on the top section, we've got 4 jacks. They correlate to the rightmost column of outputs. So fastest, third fastest, fifth fastest, seventh fastest. A nice distribution of rate, and we're actually getting a doubling of frequency as we full wave rectify. But it's full wave rectifying, so it's going to be in the unipolar positive domain. So let's explore that, and we'll be able to visualize all this very clearly as we go. So I'll add a scope in here. Just view our primary signal. There we go. And I'm going to simultaneously patch that into my compare module. So that's going into input A. If I view the max output, there we go. So these are unipolar positive or unipolar negative. Yep, unipolar negative output signals. So this one here, it's cutting off any negative portion of the signal. So this is half wave rectification. So it's removing any negative voltage from it, and we have a unipolar positive triangle peak with a flat during the negative portion. If we look at the min output, it's the inverse. So what we need to do to create full wave rectification, we need to invert this negative portion so that it peaks up in the middle. So we're folding it up. It's essentially wave folding. So we're taking this lower triangle portion, folding it up to get a new triangle wave, which will be twice frequency and offset positive. So how do we do that? The way that I did it is, we're looking for the 8 invert. Here we go, 8 vert. What I'm going to do here, I'm going to run, oops, I need to keep viewing that, there we go. So if I send my max output and min output, these are attenuverters, and because it's in the digital domain, if I set 100%, it's going to be perfectly 100%, or the unity gain from there. So that's the benefit of working these. If this is happening in the analog domain, which the actual physical expander is, there's just a little bit of wonkiness there. So this is maybe going to be a more perfect representation of what the circuitry is doing. It will be a starting point, and it goes through the practicalities, the utility of what's actually happening in the circuits, essentially. So now, if I view this one, that's our unity gain max signal. If I view the inverted minimum, we can see that's filling in the gaps. So this is our rectified negative to positive portion. So now, if we view our I'm missing a mixer, so we need to go with a 8-channel mixer. So this is a nice simple one where it's just unity gain summing. Push that there, and output. There we go. So in yellow, we've got our full wave rectified unipolar positive triangle wave. And of course, it being derived from the oct itself, it's fully dynamic. We've just created a whole new triangle wave. So 1 down, 3 to go. So there are bits that I can duplicate here. I'll need a new compare per section. It might just be easier if I just brute force this and just duplicate the whole thing. Then it gives a nice clear signal flow. Visually, I'm going to try and rebuild it in the orientation of the oct expander. Okay, so here we go. So this is our second one, which is coming from this LFO here. Let's patch that there. Send that here. There we go. Same thing. So blue and yellow. Let's go with this one here. And our last one. If I speed this up, oops. Ta-da! We have all 4 full wave rectifiers. So that's us recreated the full top portion of the octa-expander. So that's what's going on under the hood, although this has been done in circuitry, so it's with op-amps and inverting summers, but this is a way of patching up to get the same result. Yeah, quarter of the way there. Okay, I'm just going to keep moving this oct down the screen, and eventually we'll end up with a multi-row rebuild of the octa-expander. Okay, analog diode logic pairs. So I think this might be one of my favourite circuits, or just signal processes. It's a really, I think it's a very musically useful way of creating new modulation sources. It's quite. It was actually one of the easier portions to implement for the octa-expander. Took up the least space out of it. The DACs definitely taking up the lion's share of the PCB real estate. So all this is a max-min comparator, which the compare module natively does. Let's pull our cable opacity down a little bit more. There we go. Bring a new scope. Okay, let's have a look at this. Move this over so their cable's not quite as in the way. There we go. Cool. Okay, so top pair here, they match to this left channel of diode logic, max and min. So they're the faster recreation. It's actually depicted in this signal. So this was actually, I don't even think I drew this as a sort of recreation. I think I actually scoped it or tracked it into like a DC coupled into the ES9 and just tracked that into Ableton and then zoomed in and screen captured and then picked out the graphics from that. So these are actual captures of the output from an octa-expander. So this is showing 2 triangles extrapolated. So there's a slow one there and then a faster one on top. And we can see this gold line is highlighting that max peak. So it's always looking at the higher amplitude of the comparison between these 2 signals. So that's what's happening with this process. So I'm going to slow this down a bit, pull from this triangle here, send that to my A input, and then this third LFO is going to the B input. So now if I view my max signal, speed this up a little bit. There we go. So we can see anytime this lower sort of overlaid triangle wave is lower than the amplitude of the faster triangle wave, it's defaulting to whichever one's the max amplitude. And likewise minimum. There we go. So we end up with these 2 parallel output signals of max and min, which are this one and this one on the octa-expander itself, extracted from these 2 LFOs. So it's a really interesting signal process. Like it took me, like I was simulating the circuit and just experimenting with using versions of it that exist in Rack or in VCV Rack and just trying it out in different patches. But it just adds a little bit more chaos into an otherwise steady, regular LFO signal, especially when we start self-patching. So let's go with faster LFO. Get some real wonkiness coming in. If we just hide one or the other, that's a pretty cool modulation source. Likewise with the green one. So between the 2, they're both bipolar signals. They've both got the theoretical capability of hitting peak +5 or peak -5. But they're weighted because it's the sort of almost like an RMS. It's sort of weighted towards the higher amplitude or lower amplitude of it. So yeah, between the 2, you've got 2 contrasting ranges. Yeah, really fun way of patching. What I'll do, I'll match these colors. Let's go with a green cable. So this now looks identical to if I patch direct from here and overlay. We can see this is the same thing, but we have both in green. Here's green and blue. If I change this to being two blues, no, that's purple, blue. There we go. This looks like the same thing, but these are split at any contact point between the two signals, whereas these are two actual discrete signals. So if I change the color of this one, oh, yellow, same pattern, but this is more clearly showing the max and min extraction of it. Yeah, very simple, and it already exists in this compare module. But the øchd-expander does it from two groupings of adjacent LFOs. So let's add in a second compare. Oops. And it's not the lowest one, it's the two up from it. So I tried to like find patterns when I was choosing groupings for the øchd-expander. So let's go with this one here. And this one here. Oops. Oh, deleted that. Where did that go? Here. Too many patch cables. Close that, and let's go max and min. Let's keep that yellow as well, so we're matching our color scheme. There we go. So if I speed this all the way up, we can see we've got the exact same thing, but just several orders of magnitude difference in frequency. So I picked these ranges I tried a few different ones, but I thought these extremes, it wasn't the most peak extremes in terms of frequencies. A lot of the times with the Oct, I'll keep the rate control around about 12 o'clock, and that generally sits the top LFO to around that 4 to 5 hertz range, which is a really nice sweet spot for a musical vibrato. So I'll tend to keep it there, and then I know I'm going into lower magnitudes of modulation rate from that point. Yeah, but between these two pairs, it's like these are a little bit slower than my vibrato, giving me these two parallel signals, and then I've got much slower, low frequency modulators at that point. Cool, so that is two sections of our øchd-expander rebuilt. Rectifiers, diode logic. Next we're on to cascading triggers. So the cascading part, that will just come down to summing, but what this is doing, which there's a way to recreate this pretty accurately. On the actual analog, I'm pulling from the integrator circuit that generates the triangle wave from a square wave flip-flop state. I'm using that raw square, which doesn't exist on the front of the Oct itself, but on the back I was able to extract the raw square waves and work with them as needed. So we're going to be doing a bit of reverse engineering here to gain this square wave effect, and there's something that's quite particular about it. So because the circuit, it aligns to the change in charge direction, so that's where the phase of the square wave naturally lies. So the positive portion of the duty cycle of the square wave, positive one sits when the triangle is in its ascending ramp direction, and then it flips when it hits its peak. So that's where the trigger signals that come from the øchd-expander's third section, that's where they land. It's right on that negative fold. So there are a couple of ways of getting a square wave from a triangle. First up, we can again use our compare module, and let's figure out which triangles we're pulling from. It's the left column for this. So I was kind of using shapes and patterns. So top section is the right 4, cascading triggers coming from the left 4. So we've got a similar sort of distribution of frequency groupings, but it's parallel to the first section. So let's branch from here. Oops. There we go. Okay, new scope. Let's view this triangle wave. And let's view this groove. So that's when A is less than B, when A is higher than B. So this is a pretty common way of extracting a square wave from a bipolar periodic signal. This is just a comparator. So anytime the A signal is higher than a threshold, the threshold being 0 volts, the output logic is high. So this works. This gives us a square from our triangle, and to get that into triggers, we're just capping that at trigger durations. But the phase relationship is a bit off from what the original is, which may be fine, but it's not quite a true recreation of what the analog expander is doing. So there's a way to get this closer, and that is to just reduce down our offset comparison. There we go. So that's a trigger, or negative trigger, occurring at the bottom peak of our triangle wave. So if I change this to being the A is greater than B, there we go. That's a trigger signal from there. So if I just duplicate these and do this from all the related, the triggering off, so we can just see it sort of streaming. So there we go, we're getting a trigger pulse on the negative peak. So that's, yeah, that's pretty accurate to what the trigger section's doing. Let's do this one. Oops. Speed up a bit. There we go. So our trigger duration is going to be variable based on the rate of the LFO. So that's a little bit different from the analog expander, but for all intents and purposes, I think that's a pretty good recreation. Speed up once more and untrigger that. There we go. 4 trigger signals following these. So the cascading effect, it's a case of clockwise cascading normalization. Even I can never remember which way round it actually goes in, but basically if you patch it from all 4, you've got 4 discrete signals, but each time you patch from one, it breaks in a particular pattern so that you can get combinations of them overlaid together. So if you patch out of, I think it's the bottom right, you'll have all 4 of these patterns layered on top of each other, which is quite nice if you're using one of the faster ones as your fundamental pulse. It means that you get flams that sort of move in phase in relationship as the triangle LFOs phase with each other. So let's just view a combination example of these. If I add in a mix, we go. View them. There we go. So if I slow this down so that we're seeing our more regular triangle, you see that's in line. What I might need to do is trigger from this. Yeah, so we're seeing these aligning, they're fundamental clocks, where we're seeing moving patterns of these slower moving trigger frequencies, like sort of shifting through. So yeah, rhythmically you can get some interesting things from this alone. It's yeah, getting the square wave clock, or getting a clock signal from the oct, is often quite a useful utility. I like using this to ping filters, for instance, so you get this sort of stochastic rhythmic timing. Yeah, cool. So that's 3/4 of the way there. Although I feel like this section alone might give the video length so far a run for its money. R2R 4-bit ladder DACs. So I think what I'm going to need to do here is actually jump over to a circuit simulator to kind of go into a bit of the nuts and bolts of what's happening under the hood here, because it's not actually that complicated. The results are complicated because it's complex arrangements of bits going into this DAC. But I think once there's a bit of familiarity with the mechanics of what's happening, it makes a lot more sense. And I think understanding it, that's where you can predict a bit more. It's like, okay, I want a sound that is going to take bigger movements over a fundamental frequency, but it's going to wobble around that. Then you'll know which one is likely to do that based on the orientation of most significant bit versus least significant bit from the frequencies of LFOs. So yeah, it's there's a lot going on, but trust me, it's not actually that it's not that bad. Let's open a circuit simulator, clear that, and let's build an R2R ladder DAC. So I might actually need to open up the expander circuit. Hold on, see if I remember it. I built this the other day, so see if I get this right. So I have a capacitor which just smooths things over a bit. It's quite low, 100 picofarads. There's a 1K resistor on the output which helps balance impedance. There's our main feedback resistor, which I believe is 68K. There we go. Our non-inverting input's tied to ground, and then we have a resistor to ground to set a gain factor. So because this is coming from 5-volt square wave unipolar positive bits, which is how it's curated when the raw squares reach the oct expander, and then those 5-volt bits are what go into the nodes of the R2R ladder DAC. So that needs boosted a bit, so I'm pretty sure I'll go with 1 mega ohm 68K, and that was enough to bring it up to roundabout, or maybe just a bit over that 0 to 5 volt range that I was aiming for. Okay. This is where I will need to double check with the actual circuitry. Oct expander, hardware. See if I'm opening the right file here. There we go. So here's our DAC section here. And 68K, 1 mega ohm, 1K, 100 picofarad. Nailed that. I've got the op amps upside down compared to what I've drawn, but that's fine. And here we have, that's our R, and this is our 2R, so 2 times R, so 100K and 200K at each of these input points. Then there's a 200K to ground at the bottom. So that's what I need to build. Oh, actually, they're going into there. That's not going to ground. Messed that up. There we go. So this one's 200K. And add 100Ks in between here. And this last one is 200K. There we go. Okay, tie this to ground. Scoot this over a little bit. Let's draw a wire. And this is our circuit. So this is, pretty sure I have this as a unipolar positive single supply op amp. So it only needs to provide from 0 up to 5 volts. 0 to 12, and that's representative of this, I believe. Yep, 12 and ground. There we go. Okay, cool. So what is this? So this is what's called an R2R ladder DAC. Ladder because it looks like a ladder. R2R because it's resistance value 100 and 2 times resistance value 200. So yeah, it's R number 2. R is the sort of reference point for that terminology, like that. R to R. So it's R is our 100k, 2R is our 200k. And this has got 4 rungs in the ladder, so this is a 4-bit DAC. Let me show the voltage here. And what we need to do, we need to apply a combination of higher low bits to each of these states. So this is digital to analog. So digital signals being higher low, 0 to 5, and analog being our variable voltage, which in this case is going to be 0 to 5 volts with 16 discrete voltage steps, and that comes through there being 16 discrete combinations of 1s and 0s when it's working in 4-bit logic. So to quickly demonstrate this, we can actually add in a counter. Let's go with this one. That's the guy. I'll need a button to trigger this, so let's add in a voltage and a button push switch. Okay, so this way I can press this and it's going to count through our digital outputs. And we can see this is counting in binary, so all zeros, that's 0. We have 1, 0, 1, 1 1 0 0 1 1 0 1 0 1 1 1 1 1 0 0 0 0 1 and so on. So it's filling up this whole combination of bits, and there's a really cool effect when it comes to binary counters in this way, where as you're going through these steps, if you distribute the magnitudes of certain voltages, we actually get a natural count up of signal amplitude. So let me show a scope on this, and I'm going to step up at I'll try and keep it a consistent rate. Here we go. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's our result. We have steppy, but quite distinctly recognizable ramp. So that's going through all the discrete voltage steps of a 4-bit counter. So if I instead change from a direct counter, let's go with discretely controllable switch states. So to do this, I need to build in an actual switch, create a 5-volt signal on one side and ground on the other. There we go. So this is our equivalent of what's happening on this octa expander. So we can think of these as being 4 bits that are not counting in a, an ordered binary 0 to 16 order. They're randomized based on the rates of these LFOs. So at any moment in time, I could look at the oct and be like, okay, that one's high, that one's high. And it's going to be a combination of matching. There we go. So it's matched that particular orientation of high, low, 1 0 1 0, and that's resulted in a static voltage of 1.7 volts. If I change this to something else, these two, 3.3 volts. If they're all high, then this is where the mass summing of each of these, it's a ladder of voltage dividers. So summing them together with this gain value hits pretty much spot on 5 volts. It's over by 6 milliamps, it seems to be. Yeah, 5.006. So this ratio of gain keeps it accurate to 0 to 5 volt range. So how do we recreate this in VCV Rack without building a DAC and doing it in actual software? There's a way to patch this. It's a little bit clunky, but it is totally doable. So let's pull this down. This is starting to get a bit messy. What I'll do, I'll move it over just so the patch cables are out the way there, and then we'll move everything back at the end. So let's start by extracting square waves from triangle waves. That'll be the first step, and we can do that again with our compare module. So let's look at this LFO, for example. Anytime it's over, it's going to be giving me a high signal. Anytime it's under, it'll be a low signal. Center that offset. Here we go. So 50-50 duty cycle square wave. Again, similar to this trigger extraction, we managed to align a replication of the phase that exists naturally here. This is breaking the rules slightly. It means that our square waves in relation to the triangle waves are going to be phase shifted by 90 degrees, I think it would end up being. So it's anytime the triangle's over 0, it's high. So it just means that our result is going to be slightly out of phase versus the original LFOs, but I don't think we'll notice. I think we'll get away with this. So it's a little bit of a compromise, but it would take a lot more patching to get that more accurate, and the results won't really be changed unless we're measuring it in comparison to the actual LFO triangles as we're going. But this is all in the low frequency domain, so kind of doesn't matter, which is a bit of the benefit here. Okay, so let's pick these 4 states. I can even manually control this by unpatching my A, and it means that my B source is variable, so I can choose whether it's high or low. So we want to do that 4 times. And we want to combine these bits together into an equivalent of this. It's something we're going to need to derive from this as a reference point, but let's get to that. So let's add in what did I use before? I think it was just the avert. Yeah, so this is a multiplier essentially. So center position, that's multiplied by 0, so we end up with 0 amplitude. As I go up, it's up to 10 volt output, or I think if there's a signal patched in, this changes to being percentage. Yeah, so it becomes a gain when you patch a signal in. So here we have high signal. The output of this is going to scale up, and the percentage will actually correlate to the voltage. So that is 81.2%, 8.12 volts. So we've got the ability to dial in precision stored voltages, and that's important. So let's start by just matching our first DAC here, or our first DAC output, which is this guy. So if we track that back, that's coming from here. It's using this top grouping cluster of LFOs from the OCT. You see these 2 terms here, so MSB, LSB. So this is the order of bits. So if I jump back over to our circuit sim, this is our most significant bit, which most significant means if it changes state, it's going to have the most significant impact on the output amplitude. So if we go from 5 volts, if I turn this off, it jumps down to 2.3. Least significant, if I change that, we're just getting deviation of 1/3 of a volt. So each bit's magnitude from least significant to most significant has a weighted amplitude range to it. So if we look at just the LSB on its own, 333 millivolts, so that's 1/3 of a volt. If we look at this one, 667.6, so that's 2/3 of a volt, 1 volt and 1/3, and then this one, 2 2/3 volts. And that distribution, that's coming through this being a voltage divider of 200k down to 500k. So it's a 200k to 500k voltage divider, although it's a bit more complicated because it's actually going, these are to ground, so it's 100k and the rest of that. So it's 500k with 200k in parallel. So we get a lot. It's more than just a static 2 resistor voltage divider. We're getting this sort of complex pattern of the voltages, the individual bits sourcing and sinking current, which is important. That's why I've got a switch that's got 5 volts and ground on it together. What I mentioned is these particular ratios of stored voltages. So this is what I need to recreate in my VCV patch. So let's give that a go. Oops. Move that to a different window. Didn't want to do that. There we go. Okay, cool. So let's treat this as our LSB and this as our MSB. So LSB, which is here, is 333 volts. So this one I want to multiply by 33%. No, 3.3%. 3.3%. That gives us 0.33 volts. This one will be 6.6666. Depends on how many decimal places we've actually got to work with here. Let's go for as accurate as possible. 4 decimal places. Cool. This will be 13.3333. And there'll be 26.666, I think. Let's check this. So that's our 0.67. Yep. This one's our 1.3. 1.3. And this one is our 2.6. There we go. So I'm converting these 10 volt gate states to being combinations of our bit states. So this we now need to sum together. So let's use our mix. If we view this, we should be able to replicate what we're seeing here. So let's go change everything to being low. So it's 0 volts. That's all low. Let's go least significant bit. So it's this one. Interesting. That's gone to 5 volts. Why has that gone to 5 volts? Oh, because they're all summing, so these all need to be patched. There we go. If these don't have signals patched to them, they default to just being a manual DC offset. So there we go. This is us back in action. Okay, offset. Let's take this up. So we're at zeros across the board. In this case, yeah, some microvolts there. Let's add our least significant bit. 0.33. That's working. Let's just add in our next one. So that's the 2 least significant bits. That hits 1 volt. That hits 1 volt. Let's go here. 2.33. 2.3. And the last one, 5 volts. 5 volts. So this is our patched up equivalent of an R2R ladder DAC, which we can now control bitwise from any external signal. So let's go with this grouping. So we need to make sure we're matching the correct MSB to LSB orientation. So MSB is our top. So that's this one here. So that's going to go here. Next. Next. And next. and this is our resulting pattern. So this whole thing's going to scale with the frequency. So it kind of looks like almost like sample and hold, but the timing of where the patterns, it's dependent on the bits could change at any stochastic timing, because it's for unrelated or your phasing triangle signals. So let's look at this. That looks representative of it. These are actually screen captures and re-renders of actual recordings from the prototype octave expander. So they should be pretty accurate for what's going on. So this one here, we can see it's the 4 consecutive LFOs running with the MSB being the fastest. So it means that the most significant bit, so the biggest change to amplitude, is going to happen at the fastest rate. So that's where we're getting quite abrupt, big step jumps in this result, which is representative of that there. So let's just work our way down the pattern of this. I'll rebuild this one next, so I'll actually just copy and paste this entire chunk. Here we go. And now we need to figure out order. So this is MSB, LSB. MSB is our lowest this time. So we go from here, MSB through to LSB. And visually, that looks pretty apt. If I speed this up, there we go. So we're starting to see this new form of movement. We can see it's kind of, I guess, like drunk walk in max MSP. That might be a close comparison. We're getting these slower big steps as the MSB flips, but that's happening at the lowest rate out of these 4 bits. So it means that we're kind of wobbling around at smaller voltage deviations, but then bigger jumps are happening at a lower rate. So it's a very different flavor of slow noise, which is kind of the best way I sort of like came up with describing it. Okay, let's look at our next one, which is this guy. So this is again a bit weird in the orientation, but it's actually quite logical. So if we look at what sources we're coming from, these last 2 are rightmost column and then leftmost column. So rightmost column, we've got our fastest and slowest rates, and these are ordered so that the fastest one is the least significant bit. So we've got the fastest movement applied to the smallest deviation in voltage. So let's branch from here. Oops, that's not what I want. Here we go. So fastest is going to least significant bit, which is our leftmost in this example. There we go. And then this one, then this one, then this one. Cool. So if we look over here, that's kind of a zoom in of it. So if I slow this down, there we go. That's a bit more representative of it. I'll be able to get us a rate that kind of closely mirrors these depictions. So same process, different sources for rate of bit changes, and we're getting very different flavors of stepped random or stepped slow noise. If I speed this up, we can kind of see this pattern emerging when it's viewed more condensed over time. We're getting sort of, it's almost like Alberti bass. It's like oscillations between notes, and those are changing up and down based on the slower changes, which are the most significant bit happening at the slowest rate. So it's kind of a hybrid almost of these 2 approaches, where we've got this sort of micro movement or slower macro movement, of bigger steps from the slow MSB. The LSB being faster but distributed across this deviation. We're getting like orders of magnitude and difference of rate of our bits themselves. So yeah, really different ranges of signals. So let's add in our fourth lot, just to be a completionist. This one looks the cleanest of it all, so it's the leftmost column. MSB is the fastest, LSB is the slowest. So let's go from here, so that's our fastest. Oops. And that's MSB, which is this one. Then here, then here, then here. There we go. If we zoom in, that's, I think it's down to our rate. Let's slow this down a bit. There we go. So we've got some big jumps because we have the fastest of the bits going to our most significant bit amplitude. Nice. And that is it. That is our recreation of our DIY version of the Oct expander. So that's quite a lot of modules. I mean, even if I remove the scopes, that's still quite a lot of patching. Yeah, let's view this a bit more realistically. That's what we're dealing with. That's a lot of stacking cables. Yeah, not the most efficient thing. So that's where the Oct expander itself really shines, is how much I was able to condense this down and get this efficient, because I really didn't want to go too far with the design of this for an expander for the Oct and add things like VCAs or sample and holds. The challenge was using as much of what exists as possible in very efficient ways, and I think I managed to strike a good balance of additional modulation output sources derived from these existing 8 analog LFOs. So yeah, hopefully this video was not too boring. It's a little bit scientific, a little bit logistical, but hopefully that sheds a bit of light on what's going on under the hood, and looking at examples of diode logic, full wave rectification, logic extraction, and then DACs are fun. Like they're everywhere, but like this I thought was quite an interesting use case of it in the modulation source domain, which is 4-bit, so low bit depth resolution, but kind of doesn't matter. It's just you can kind of use it as noise. So like using these signals into a sample and hold or into a quantizer, that's kind of my go-to patching approach of it. Yeah. So there is actually, I'm not sure what version of the build I'm running here, but let me just test something. If I quit Rack just now, there was an update on the internal Discord server, which I've not actually done anything with yet, but let's look at this. Let's clear that. There it is. Okay, so I've actually got a new installer. So if I reopen Rack, I should have cleared that. Let's start that again. This should have no Instruō modules. Cool. Okay, so I need to drag this test build. Close Rack once more. Open again. Okay, so this is a latest build, of course, so that's running on the latest 2.5.2. We now have the CSV2, so that's now virtualized, and of course, there it is. So everything that I just did in this video was kind of redundant. hopefully this was useful in any case. But yeah, there you go. That's the auto expander is now in VCV Rack. You need not build it from component parts like I just did. But yeah.